Welcome to the introduction of circular motion, which starts us off with Unit 3, which is going to be fast, sweet, and kind of important. Even though it's only like less than 10% of the AP exam, it's the thing that they're going to slide in every now and then to try to trip you up. So let's go ahead and get through the basics. Now think about this question. What makes you turn? Think about when you're walking to class. You're not walking in a straight line. You have to change direction every now and then. How do you change direction? No, like literally, physically, what do you do with your feet to cause you to change direction? Break it down. Stand up and walk and do it in slow motion. How do your feet push the ground to get you to turn? This should always be our first question. Whenever we're dealing with a problem where the direction of motion is changing, so I don't mean back and forth on a line or back and forth on a line, but I mean I was going like this and now I'm going like this. I turned. The first thing we need to ask is, what is making that object turn? Okay, so first definition of turning. Turning is whenever your velocity changes direction. So maybe you're still going the same speed. You're going 5 meters per second and then 5 meters per second and then 5 meters per second and then 5 meters per second. But the direction has changed. Within the confines of this class, that is always going to be a circle. We are always going to be dealing with turning that is a circle. So when you turn, that is when your velocity is changing and you start going in a circle, or a part of a circle. So, but if you turn, your velocity just changed. I mean, it was the direction, so the number stayed the same, but the direction changed, which means your velocity changed. So what is it called when there's a change in velocity? Hopefully, that was enough time for you to remember. That's called acceleration. We already have this in our notes. The acceleration is defined as the rate of change of velocity, the change in velocity over a change in time, delta v over delta t. Okay, but if there's an acceleration, what's causing the acceleration? That should have been enough time since we just did this. An acceleration is caused by a net force. If there's an acceleration, there must be a net force. There's no other way. So here's your summary of everything. A sum of all forces must give us net force. Note that means vector notation, vector addition, not adding up all the numbers necessarily. Normal force and gravity force, those you would add together. But normal force and applied force, you would not add those two together because they're not in the same direction. For these two, you would need to use vector addition to get a diagonal net force. All right, but whatever you do, you add up all the forces, you get net force. Net force is also going to be equal to mass times acceleration. Little note, since this is a mass of a moving thing, it's inertial mass. If it was just gravity force we were talking about, that uses gravitational mass, which is the same thing, except it isn't. Don't worry about it. So we know for a fact, based on what we already know, if there's a change in velocity, there must be an acceleration. And if there's an acceleration, there must be a net force. All right, so then the big question becomes, what is the net force that makes you turn? What is that force? How could we mathematically describe the force that does not change your speed, just changes your direction of motion? Interesting. So what makes you turn? With this in mind, think again about walking to class. All right, there's a big group of people on the way, so you have to walk in a circle, half circle, around them. As you are walking in that circle around them, what are you physically doing with your feet to make you go in that circle. Whether you realize it or not, you are pushing yourself inwards towards the center of the circular path. When you are going this way, if you want to go that way, your velocity is going to do this. That takes a force. This is the force that makes your velocity change. So as you are walking, you're literally taking your outside foot and you're pushing a little harder with it than normal, pushing yourself in to the center of the circle. Now, your forward momentum plus a push in causes you to go forward and just a little bit in, but also it turns you. You repeat the process with each step, and you find yourself walking in a circle. All right, interesting. This is always true. Whenever there's circular motion, that means there's a net force perpendicular to velocity. Whenever you have net force perpendicular to velocity, you're going in a circle. It goes both ways, always true, always, 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 actually always. All right. Now, in this unit, we're going to be dealing with a bunch of different types of circular motion, and then we're going to deal with kinematics while going in a circle. Yeah, that sounds exciting. Today, we're just doing the basics, what I call a standard horizontal circle. We will also be dealing with a banked horizontal circle. More on that later. Then we'll be dealing with vertical circles, like a loop-de-loop on a roller coaster. Then we'll talk about gravity and orbits. Now, in reality, most planetary orbits aren't circular, though they're elliptical. But if we focus on planets and their moons, those are largely circular orbits. And as we will see, the elliptical orbits are really just circular orbits that have been stretched out a little bit because the numbers aren't quite equal the way they should be. More on that later. All right, so let's explain this picture. There was a really popular toy once upon a time. It's literally an airplane on a string. Now, the cool thing about this toy is that if you took the string and you whirled it around your head, or if you turned around in a circle fast enough, you would be giving the plane enough forward motion to create the lift it needed to start the fly. So without any electricity or motors, you could have a toy plane that would fly in a circle around you. And it was tied to a string, and as long as you kept doing this to it, it would keep going in a circle around you, flying. Really cool. Now, let's look at that. We can see here that as the kid is swinging the plane is changing direction. The velocity is changing direction. Its speed stays the same, but the velocity changes direction. It's turning in a circle around the center point, which is the kid. All right. We know that whatever forces are on that plane, the net force must be equal to m times n, just because that's always true. We also know that there are three forces on this plane. There's gravity force, there's normal force, lift force, technically in this case, but we don't care about those right now because they cancel each other out. So, which leaves us with the third force, is the only one we care about, tension force. The plane is going in a straight line, and then it gets pulled 90 degrees from its direction of motion. This causes the velocity vector to stay the same magnitude. So you're still going 5 meters per second. But now instead of 5 meters per second that way, you're going 5 meters per second that way. And then 5 meters per second that way. And then 5 meters per second that way. So on. Ooh, interesting. Now, the math works out to give us this equation. When you have a net force perpendicular to velocity, you go in a circle. And when you go in a circle, that acceleration, which is describing not a change in the number of velocity, just the direction of velocity, that acceleration that's just changing the direction is equal to your speed squared divided by the radius of the circular path. Interesting. Let's put all that together, shall we? We know what the net force is in this case. It's the tension force. That was easy. We know what A is because if it's going in a circle, it's always going to be V squared over R. Which means that now we have an equation about this scenario. The tension force must be equal to m times v squared all over the radius of the path. Not the circumference of the path, not how long the path is, not how long it's been flying, but the radius of the path, not how far the plane has gone. Now that's weird. This holds true for literally any situation where you have an object going in a circle and that circle is horizontal. Literally doesn't matter. Here you have a really, really brutal freeway on-ramp. We have a few of these. We also have some brutal off-ramps in the area that are pretty sharp turns. They feel a lot like this. What's causing the car to turn? What is that red force representing? What makes a car turn? Okay, well, I know that my wheels go like this normally, and then when I turn the wheels, I start going in that direction. Okay. But what's doing the pushing there? This one's hard. So instead, ask yourself this. What happens to the car if you go too fast around a curve? Like, really too fast. If you're just going way too fast around a curve, what happens to the car? It spins out. In other words, the car slides, instead of rolling, over the road. The car spins out, it's no longer on the road. In other words, whatever force is supposed to be this red force, keeping you in a circle, could not be enough, and your car slid. What makes you move in a circle, be it when you're walking, running, or in your car, or on a bike, or anything, is the static friction force. Because the static friction force says, hey, this car wants to go in a straight line. But its wheels are like this, which means that the wheels can't turn like that, and it doesn't work like that. The tires would have to skid like that to keep going in a straight line. Static friction force does not like skidding, so it stops the skidding from happening. If the skidding can't happen, the wheels do the only thing they can do, which is roll, causing the car to turn. All right, so let's look at this. This means that I got gravity force down, I got normal force up, I got a static friction force to the left, preventing my car from skidding out. Yeah? The car wants to go in a straight line and leave the circular road. It is static friction force preventing the tires from skidding, preventing the sliding, thereby causing you to go in a circle. Which means that my mv squared over r thing, still true. That must be my net force. It must be my net force because I go in a circle. But net force is also going to be equal to the sum of all forces. In this case, that's static friction. Okay. Static friction is the coefficient of static friction times the normal force to get the maximum. We're pretending we're going as fast as possible on this curve. And we know that normal force is m times g, assuming you're, flat. If you're on an inclined plane, things get weird. Let's not worry about that yet, shall we? Which means that now we have an equation that relates what's going on in this picture. The coefficient of static friction times the mass of the car times g is going to be equal to the mass of the car times the speed of the car squared all over the radius of the path. Not the length of the path, the radius of the path. Interesting. Now, of course, the m's cancel, right? But we still figured it out. We now have an equation that we can use to solve for whatever it is I ask you to solve for. Last example, and then I'll shut up. One of my favorite fair rides, and it's called different things. Gravitron is the one that I'm most familiar with, but it's a big room that looks like a UFO. And you're in the room, and then the room starts spinning around really, really fast. And as you're spinning, you start going, whoa, and you feel like you're plastered up against the wall. And you're plastered up against the wall so strong that you can lift up your legs if you want, and you're stuck on the wall. It's really cool. It's tons of fun. The one that I'm most used to has angled walls. So the spinning slams you against the wall, which is angled. And then turns out that this angled wall has wheels on it. So you actually go, whoop, and you end up at the ceiling of this weird spinning room. And the only thing holding you up, what is holding you up? Look at the diagram. If that guy is going in a circle, there must be a force towards the center. Okay, yeah, whatever. Let's ignore that for a second. The guy isn't falling. So there must be an upward force. What possible force could there be that's preventing this person from sliding down the wall and hitting the ground again? Good old static friction again. So we got gravity force down, static friction holding you up. Weird. So the room is spinning so strong that you're getting slammed into the wall, so strong that the normal force is so strong that the static friction force is so strong that it cancels gravity. It's nuts. I love it. But that means that now my net force is the normal force. Because static friction and gravity have to be canceling each other out. Otherwise, I'd be flying away or, falling. Since I ain't doing either of those, normal force must be my net force. But I'm going in a circle. So my net force must be m times v squared over r. Okay. We know the static friction force must be positive mg, where gravity is negative mg. We know static friction force is mu s times normal force. And we know that that must be positive mg, which means the normal force must be mg over coefficient. Okay, which means now I can take that normal force and plug it into my second line and get an equation that relates what's going on in this problem. That says, all right, well, mass of the person, gravitational acceleration, the coefficient of static friction between my back and the wall holding me up, that must be equal to my mass times the speed at which I'm going around in a circle squared over r. Interesting. But keep in mind, every time I've been talking about the v, I've been talking about my linear v, the actual velocity of what's on my speedometer. If I back up, the v I'm talking about is the speedometer speed. It's the what's on my dashboard. But of course, if we're going in a circle, we might want a different way of describing motion. Let's worry about that later as well. Congratulations, you survived the introduction to circular motion.